Hello. Hello. Okay. Hello, everyone. Thank you for attending today's workshop. We'll start a few minutes. I think there are already 5 viewers at the moment. So maybe we give a few more minutes to others to arrive, and then we can start. In the meantime, if you have some questions, please place them on the Slack channel, and we can go from there. How was this week? You guys have fun with the exercise? All right, good, good. Any questions related to the lab? Yeah, I can go through the lab first. That is typically what we do. So the question is, can we go over some of the second lab part, the the second part of the lab that relates to RDDs? So yes, certainly we would do so. But at this point, yeah, most people know about RDD, so we might not get into full detail, given that we have covered some of it. But given that the topic is sort of like a review of math and RDDs, yeah, sure. If you have specific questions about RDD, Chris, maybe you can ask them as we go as well. Is the quality of the recommendation also based on how our ratings were distributed? Yeah. Yes, that is the question is how does the ratings how do ratings affect recommendations? So what that means is if you're a person that typically rate everything very high versus somebody who rates everything very low, you might get different recommendations. So yes, and there are solutions for that. So you could do something called the baseline recommendation, or scale all your recommendations based on some sort of baseline. And what that means is, say, for each user, you might take the mean of the recommendations, and then you add just whatever change occur on top of that. So that in a way would help you reduce that variance that you have when different people have different sort of scale for grading. And similarly for the other side, for the movies, you could also reduce the effect of this by taking the average. I mean, that is one way to do it, but certainly there are others. And then, of course, ultimately, what happens is the recommendations are based on other users having sort of like a similar profile. Remember that, well, what you would have is a vector representing your patterns, and then you find users that have a similar vector. So then that could be that is actually more important. But certainly a baseline for each user and each movie is something that you should consider when doing a real recommender system. All right, so let's start with the with the lab for this week. So let me go to my home directory. So I'll make it a little bit bigger. So this week was about math, NumPy, which is a numerical library in Python, and lambda expressions, which in a way we have been using. So a lot of it in a way is a review, or probably this lab is in a way misplaced. Probably should have been done this first or second week. But nevertheless, I think it's important for what's coming, what's more focused on machine learning, where you're going to start seeing more of these sort of operations. So the first part, I'm going to go rather quickly. So how do you do dot products? You guys have done some of that for the previous week already. So in matrix multiplication, in a way, it's already implemented in other libraries, and that's what you typically use. You use something like NumPy to do those multiplications. So there are examples. I think is very, very clear. Unless there is a particular question about NumPy or how does it differ from other sort of structures, we can skip this part. But I find it was very straightforward, right? You had a matrix, you could calculate the transpose, you calculate the inverse, etc. And that is, so let's focus maybe on the RDD part. And so this starts with this dense vector, which is a representation of a vector, particular in PySpark, and it's used to store arrays. And there is the dense vector, and there is this sparse vector. And there are already a lot of the similar functions that you would find in a regular NumPy array. You can also find them in a dense vector, similar for the sparse vector. As always, if you have any questions, I gotta watch this video. What? Sorry, I think there is a message from Agustin where it says, I got watched this video on YouTube, playback on other websites has been disabled by the video owner. So what that means is that you have to open it on YouTube. I see it here. Has been disabled. So if you open the link directly on YouTube, that's fine. Otherwise, you can. Okay, good. So, and that is what we have, right? So, for instance, things like the dot product already implemented. So that's what we see here. We define a dense vector, which just takes a NumPy array, and we can calculate the dot product with a NumPy vector, for instance, or another dense vector. We get to lambda expressions, which are in a way shortcuts for functions, and you guys have done this plenty when doing maps, filters, etc. before. So this was in a way a very brief review of that. So the example is, and I think we had a lab where we wanted to add the plural to a word, and what we would do is add the character S at the end of the string. So similar, the same representation can be done with this anonymous function. So these are functions that in a way don't have name, but the beauty is that it can make writing your code less verbose. So then sometimes that means easier to read. Unless there is a particular question about lambda functions, please do it now, otherwise we'll continue. So certainly what this would do is reduce the number of lines that you write of code. So this is the example of defining summing two values, x and y, and the similar version would be something like this in a lambda function. So this is sort of more of the same, a little bit. How do you define it? How do you invoke the lambda functions? But we can skip that. Let's see. Now we'll get into the functional programming part, which, with the help of lambda functions, you can do some of that in Python. So what that means is, for instance, in this case where you have a data set, you're going to apply whatever is the result of this function. You're going to apply another function, which in this case is a map. So remember, so this data set was built by taking as input a range. So that is a sequence from 0 to 10. And then we're multiplying each one of the items by 5 with this lambda function. And that's how we get this value here. So instead of 0, we'll have 0 times 5, which is 0, and 1 times 5, 5, etc., until 9, which is where the range ends. So then it becomes a very useful tool for doing this sort of large-scale data analysis, when you can do small operations on your data and do transformations that then you can later reuse. I think, Chris, this is maybe a good time if you had a particular question. Address it now. But for instance, this data set could be, it's a particular class right now, but it could be an RDD. And let's say this particular RDD just has one element on each one of the rows. And that element would be, let's say, row X. So then what you're doing is you are converting, you adding 2 to each one of the elements by doing the first step, the map. And then the reduce, what you do is would combine each one of those maps. And here you say, how do you combine? So if you have 2 elements, X and Y, you would combine them by multiplying. So okay, thank you for, so Vlad shared a link of what not to do with lambda function. So that's something you guys can read on your own after. But in a way, this is something you have already built upon. So taking applying different functions on RDDs or different sort of a structure, as well as map reduce filter is more to do with building functions for grouping and aggregating. Correct. All right. So I guess that was a statement, not a question. Fine. So unless there's some more questions, we can go into the we can go directly into the exercise, which was the movie recommendations. So I give you a couple of minutes. Otherwise, I'll jump in. So in the meantime, I'm going to prepare the cluster for the other, for the lab. Sorry, for the exercise. Here, this one here. So I'm going to create a cluster. And here we're ready to go. So certainly most RDDs are not just one column. You might have different columns. So how do you want to access each one of those elements? You could treat it as an array. And one thing that I always recommend is look at the API. So that is something that you can, so I'll make this a little bit bigger. If you look at RDD, we can go to here. And actually there's a little example that can help you understand further. So here is an example of map. So again, this is just one function. Sorry, this RDD just has one column, so it's pretty simple. So you generate an RDD here, and then you map the result that to a number 1. So this is the typical setup that we've seen for counting words. Let's see, JJ has a question. I'm curious how to get those hash values. How to get those hash values. Sorry, was this in the lab or where was this, JJ? Can you tell us? Something you saw in the lab? I'm trying to open it here. Or in the lab. Oh, I see. So 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 this is a way to just check that I think I searched for that hash value and I have that on the screen. So what it's doing is converting this vector or this object Z into a hash number, into a hash. So what that does is a mapping that you don't know what the mapping is. So that's why I don't think you can get this hashing. So for instance, if we attach this to this cluster and we run this, let's see. Oops. So it's all below. So that is that. There it is. So just 1 second, please. So I'm trying to look for an example of a hash function. Okay, so something like this. So what you're doing is each one of the objects, so let's say you have 3 objects, and you pass them through the hash function, it will give you a unique identifier. So they already pass this array through the same hash function, and they got this particular value. So it's very unlikely that there is a collision. So if you were to do another value of Z instead of 18, maybe only 8, you will not get the same hash. So that is a one-way transformation. So from the hash, there are ways to go back to the original input, but this might be a bucket. So several inputs could hash to the same value. So that is that there is a collision with the hash function. So there is no way really to get from, or at least in this particular example, to get from the hash to the input. It's just a one-way function in this case. All right, I hope that was clear, JJ. Otherwise, we can discuss more after. Okay, so movie ratings. So yes, definitely there are many ways of rating movies, and people have spent years even just going for the full grad school just on recommender systems. So this, in a way, is a very simple version of a full-scale recommender system. Nevertheless, ALS is an algorithm that some people use. There are some reasons why in practice might not be the most efficient way, but we can get into those details after. So in this case, we have 2 tables, one that contains movie ratings, and the other one that it contains the movie's information. So I always like to first examine the data set and what is inside. So while the first functions, you didn't even have to write them, but what it's doing is extracting. So this is pure Python. There is no Spark involved up to this point. And what you're doing is splitting the string onto this particular group of characters, so 2 semicolons, and then taking each one of the three values. Similarly for the get the movie tuple. So let's run that. And what that does is it tells you that, yeah, movie one, user ID 1 rated movie 1193 with a rating 5. And then on the movie side, it's just simply telling you that the movie 1 is actually this representation, Toy Story. There you go. So there you go. So the hash. So I think there were some more explanation about hashing in the Slack channel, so you guys can get into more detail if you feel that it was not complete. So then, as I said, I always try to look a little bit more what the data contains. So in this particular, I just do take, which would just take the first 10 elements of the RDD. So the ratings, we know that all this correspond to the same user. So one user could be multiple times in the same RDD. So it's rating rating many different movies, and then of course having different ratings. So this user, it looks like from, so let's say what happens if we do take 100. We can filter by that user. So just a quick, it looks like this particular user 1 likes to rate everything high. So that might be a problem when it comes to rating things that maybe other users don't have the same level of rating. Then let's see, movies RDD. So there is not much to see there, simply that it's an encoding of each one of the titles. So then, right, so here is an example of what the effect of doing parallel computations. Sometimes the results that you get when you perform parallel computations might be different as if you perform it in series. So in this particular one, you have two arrays, each one of them containing a key, which is a numeric, and a string. So then if we parallelize this, each one of these arrays, and then we sort by the key, we might, given that there are repeated keys, so for instance, the key 2 is repeated 2 times, and the key 1 is repeated 3 times, we could get different sortings. I think it could be that because we're running just one machine, we're gonna get the exact same sorting sometimes. Even in parallel, it could be that they're the same. But you could see here, for instance, that the first array, yes, all the 1s are before the 2s and before the 3, but they're not necessarily in the same order. So that is something you consider, especially here where we're going to be doing a lot of joins, and we're going to be, well, actually for the join doesn't matter, but for ranking of objects, you might fall into, or you might think that there is no match, or you don't think you find the proper one. So for this, to solve that, you could do is in a way convert this tuple of 2 into a tuple of 1, and then sort from that. And this is what this next function does. So it simply appends them together, and then if you were to sort, you will get the exact same sorting. So that is sometimes, yeah. For instance, when you do group by, and then you do operations within the group by, those operations, if they depend on the order, for instance, you take the first element might not always be the first element, or it consistently won't be the first element always the same. So that is the sort of consideration, say, for instance, if you're working with time series, where the timestamp is important, you might want to do something like this, sort of to append the key to the value before you do the sorting. So in a way, you're sorting by the key and the value at the same time. Okay. So so the first sort of recommendations that is suggested here is to, if we recommend the most popular, if we in a way try to figure what is the average user would be the one that would like the movies that are rated the highest. So an easier recommender would be, well, let's find out what movies this particular user has watched, and the users that are highly rated, and then subtract the ones that are the most highly rated and the one that the user have already watched, and let's just recommend that. So in principle, it should work for a lot of the users, but it is not personalized. In a way, we recommend the exact same thing to everybody. But nevertheless, it would be certainly we're recommending the most popular, and there is a reason why they're the most popular, because people are certainly rating them highly. But we want to make sure that we in this nowadays we get recommendations everywhere. I want to make sure the recommendations that we get are the right ones, right? So when we go on Monday and check our Spotify list, or the recommendation list that we get from Spotify on Monday, we want to make sure that we get surprised and we actually see things that we like but we have not seen before. So that is certainly important, that we get the right recommendations, not just what everybody else would be getting. So this one, this first function calculates the average rating. I don't think there would be many problems there. So what we do is extract each one of the fields. So we extract the movie, we extract, let's see, one second here. All right, so we at this point already there is a tuple that is being built, or we at some point we will build a tuple that will look something like this. For each one of the movies, we're gonna have all the ratings in one tuple, where the first element of the tuple is the movie ID, and then the second element is all the ratings. So given that that is the structure that we would expect, the movie ID would be the first element of the tuple, and the ratings would be the second element of the tuple. And to find out how many there are, you would take the length of that array, and the average rating would be the sum of all the ratings divided by the size. So I don't think there was any problem there. And so once we can check that our results are passing all the tests. How do we find then, given that we have that tuple structure, how do we find the movies that are the highest rating? So we have initially our data set looks like we already know: user ID, movie ID, and rating. And we want to convert it to a tuple that has there are some questions here. That has the structure that the function that we wrote before, this get counts and average would expect. And that is what we do here. So we take the ratings, and then for each key, so for each movie, we put together the ratings. Sorry, yes, and then we group by key. So all the ratings are grouped into one tuple. So we can run that. Any questions up to this point? All right, no questions. Good. Oh, Chris, you have a question. Instead of group by key, I use group by. If I had to specify the key to be returned in the group by via the lambda function, should the result be the same? I was getting the same result. Yes, yeah, the result would be the same for the reason you explained. So I think, yeah, you solve your own question. All right. Anybody wants to add to that? Let's see. If I had to specify the key to be returned in the group by. Okay, Chris, maybe we can look it into detail after, if that's okay with you. But let me see. So what you were doing instead of doing this group, like, so what we can actually try to give it a shot now. Why not? We're doing good with time. At cell below. So at this point we have ratings. Right, we have ratings, and let's take 3. And then what we're gonna do now is we're gonna map. We're gonna map lambda x of 1, x of 2. What is this? This object has not true map. Oh, I see. Right. So this, what it converted to this tuple was the tuple of key, which is the movie, and the rating. And then what you suggested, so we do, if we do like the example, right, group by key, we're going to group by first element of the tuples, right? But say if you do group by and then you do lambda x of 0, yeah, get the same result. Because you're effectively, you're saying what the key is. I don't know if Chris, if this is what you were trying to do, or what you did differently at this point. All right. We're gonna leave it there, and we can go back to it in more detail, Chris. But I think you should get the same result because you're effectively selecting the key as your grouping. So I think, yeah, the result is the same. If there's a mistake on, please, anybody who can see it, let us know. Okay, next we'll look at. So now that we have this D and movies with ratings, right? That we have prepared here, this RDD here. What we can do is join that back with movies RDD. And then what is the purpose? That then we can do operations on that newly created tuple, right? So we have, let's see here. Right. So what we created here was the ID, the name of the movie, and what is this? I think I'm lost here. Okay, let's go back to the instructions. All right, I see now. Oh, I see what it did here. I see. I repeated this. So typically, sometimes when there are these transformations, you might get lost. So what I like doing is sort of doing them in little steps. So first I do the join of movies RED with movies IDs with average ratings. And then I do the mapping. Yes. So if there's any questions here, please let me know. But this in a way was my way of understanding what is the processing that I was doing. If you have a large data set, you might not want to do this, but you take a small sample of your data and then do these operations before jumping and doing them with the full data set. But this was small enough that it was not a big deal. All right. So at this point, what do we have? So we have the RDDs of the movies with the highest ratings, and we can determine which are the top 20 movies. But we want to filter those that were rated by at least 500 people. So we can see what is the content of this RDD. Right, so here we have the number of ratings, and here the average rating, and here the name of the movie. So the first thing we should do if we want to filter those that have more than 500 ratings is to filter by the last element, so the third element of the tuple, which is done by this function, this filter. And then the next thing what we do is we sort, and for that we use the sort function that we wrote at some point before. Where's it? Right. So this is the sort function where we put together the key and the value, and then sort by that. because the key in this case would be the rating, um, and the value would be the name of the movie. And that's how we were able to get the top rated movies for those movies that receive at least 500 um, 500 rating examples. Any question up to this point? All right. So if these are the most popular movies, those are the ones that we can then start recommending to people. The next, we move to collaborative filtering. If there is any questions up to this point, I mean, I think at this point you guys have done a lot of mapping and reduced functions. So I think all the operations up to this point were very straightforward. I think the second part gets a little more interesting because you get to use mllib, and then we can get into some of the details required to successfully running mllib. I think the explanations here are very brief and I get to the point. So I hope you guys had a chance to read them. But yeah, there is this matrix where you have users and you have items, and then you have in the middle of, or in the intersection of those two, you have a rating, whether the user liked it or not. And that could be applied to many different places, not only movies, but certainly marketplaces. When it comes to places like marketplace, for instance, if you're buying a product, there are ways to explicitly collect the rating, whereas the user bought a particular item and then gave it a rating, so a number of stars. But also we can find other ways of coming up with this rating, and this rating could be, for instance, whether the user have browsed the item, whether the users have bought this item. So there are, in a way, alternatives or explicit ways of showing that you would rate this particular item highly by looking at the browsing history and how the user is interacting with this particular item, or maybe items that are in a way similar to this one particular. So then those are different ways of building this matrix that has on one side the number, the users, and in another side the movies. And one way of solving the problem, so this matrix will be a very sparse matrix, which will only initially contain the values for which the user has interacted. So whether they explicitly rated or implicitly you found some way to come up with the ratings. And the idea would be to decompose this matrix into two matrices, one that only contains the information of the users and one that contains only the information of the movies, or in a way encodes the information of the movies. And then whenever you would multiply these two matrices, this approximation would give you back the ratings. And then you would, in a way, get filled back all those zeros of this sparse matrix that you have initially. And the way to solve it, there are many ways of doing this decomposition, but one way of solving it by using this alternative least squares. And what you do is you initialize randomly, say, the values of one of the matrix, and then you minimize. So this is the mean square error for the matrix, sorry, the mean square error for which is the cost function for this particular problem. You minimize this problem, and you find the weights that minimize this particular cost function, and then you alternate, then you fix those values, and then you start doing the same sort of operation, but for the other matrix. And then at the end, this result would converge in the way that when you multiply these two matrices, you will reconstruct the main matrix. There's a coefficient, lambda, That is the penalty coefficient. And then here we're using the L2 norm. And this, what it's doing is penalizing heavy weights. So and this, what it does is prevents overfitting. If you find that maybe one of the weights is carrying too much importance, you can reduce the importance of this of that particular weight by using this penalty function. So if you think about it, if this weight were to increase, this cost function also increases. Therefore, it won't be minimal. And then what you want to do is minimize this particular function. So then that's what ultimately this penalty value is doing, reducing or preventing those one weight to just take over all the others. Are there any questions up to this point? All right. If not, then let's just continue of actually how do we solve this particular problem. So whenever you are solving this sort of machine learning problem, it's a good idea to split your data set. So you learn from one part of the data, and then you check whether your algorithm is able to generalize in the second part. So that's typically called the testing. So you could, some people would see it as two, where you have one for training and one for testing. So this testing data set would never, or the algorithm, when it's being trained, will never see the data that is in the test. And then further, you could split the initial training set into two, one training and one validation. So validation could be used for things like no video. All right, let's see what happened with the video. Oh. Did it go back? Oh, it is blank. I see here in my screen. Maybe I'm gonna stop the screen sharing and do it again. Please let me know if it is back. All right, cool. So, so I was saying that typically you want to have or split your data or whatever data you have available into subgroups. One that you use to train the model and learn all the parameters related to the model, and another one that the data never sees. And then that is to evaluate the performance of your model, and more importantly, to see whether your model could generalize. And this not only applies to recommender systems, but for most machine learning algorithms. Of course, there are different considerations when you have, say, for instance, a small data set. So splitting in a way could be forbidden, but there are other ways around it. I think we might get at some point one of those. Not in this week, but some point later. We can talk about what do you do when you have very small data. But given that we're talking about big data problems, in principle, that is not an issue initially, but there are times where you have that case. So yeah, so here we're splitting the data set, and we're doing a random splitting, and we are taking 60%, 20%, and 20% of the data. And let's run this bar here. Oops. Okay, so sorry, one thing to mention is the random seed. This is important because given that it's a random split, if you have the same seed the splitting, you will get always the same split, and that's important for this sort of problem where you are expecting everybody to get the same results. So if you, for instance, were to split the data differently, you might get different result, or slightly different, hopefully not too different. But since we are all hoping to get the exact same numbers, that is why you have a seed, initial random seed, which, when you want to talk about being able to reproduce your experiment, that is also a consideration to have if you include any randomness in your algorithm. Then the next thing we do is build the function that we're going to use to evaluate, and this particular function is the root mean square, and this is the formula for the root mean square. And what it's doing is taking the difference between the predicted value and the actual value, taking the square of that, taking the difference between the predicted value and the actual value, and then squaring that and dividing by the total number of elements, and then taking the square root of that. So what happens is, imagine if you always predict correctly, what that means is that the predicted value x is equal to the actual value y. So therefore this number will be 0. So what that means is, the smaller the error, the better your prediction is. So I think there's a question now. Can you talk about cross-validation and how it might help dealing with the situation when you have a not that big, smaller data set? Yeah, that's what I was referring to before. So certainly, yes, if you have a lot of data, that is all great. But even there are times where when you so let's actually, I think an illustration will be better. So I do bigger. So there are alternatives of splitting your data set in the typical somewhere like 80-20 or 60-20-20, like we were doing here. So you can actually split the data set into even a number of folds, let's call. So for instance, let's say you split it in 10, and then what you do is you train a model with 9 out of 10 parts of your data set, and then you repeat the model taking out one of those chunks. And then what you do at the end is you average all those elements, all those models, or the prediction of those models into as if it was only one. So this is the extreme case where you don't have, in a way, if you have a very small data set, you can remove the testing, and then you are, in a way, training different models by holding out different parts of your data. And then by averaging them, you are reducing the variance of each individual model and the chances of overfitting. So think about it. If you train just one model with the full data set, you don't know whether your model is good or not because you never evaluated it. While when you do it in this fashion, what you do is you can evaluate the performance of the model that you train with the first part with the second part. So this is the extreme case of cross-validation. But say, for instance, you want to also tune the parameters, which is a place where people use cross-validation often. Similarly, you leave part of your data set out, you train your data with the first part, and then evaluate the model in a particular part of your data that was not seen by the training set, which is the first one. So in a way, is doing the training and testing split again. which is exactly what we were doing here. We are taking 80% of the data for the training, and then the testing is the second part. I don't know if that is something of what you were looking for, Agustin, or if you have a further question, we can certainly go into detail. This is a very interesting topic and very, very useful. Okay, good. So we already split our data into 3 subsets. So let's just rerun that. And now, since we are going to evaluate, we have to, when we're training an algorithm in machine learning, typically there is a cost function. And the idea would be, correct. In particular, what you do is you have to come up with some sort of defining what is that you want to minimize. So in this case, we will minimize the root mean square, but there are certainly other metrics that you could minimize. So you have predict, so to compute the error, predict the ratings for each movie and user, where the entry is of the form movie, user ID, movie, and rating. And there are 2 RDDs, one predicted and one the actual, and the 2 have the exact same format: user ID, movie ID, and rating. And we want to make sure that for a given user ID and movie ID, we can take the difference of the 2 ratings. So that is, in a way, I think, given all that you guys done, very straightforward. We take the initial tuple and we convert to a tuple of user ID, movie ID. And then what we do is we take the difference of the rating and then square it, which is done here. Right. So what we do is, in a way, reformat the initial input into a different sort of tuple, and then find out what is the mean error between each one of those tuples. So what do we do? Maybe that's a question. What do we have to do a join here? What do you guys think? Errors. What is this join doing? So I guess that is a question. Question for audience. This, oh, sorry. This one here. Correct, yes. That's exactly. So we want to make sure that in the same row we would have the same movie and the same user ID, so we can do our subtraction correctly. So this function, I don't think there was so much complication coming up with the answer for that. So let's run that. That looks good. And let's run this test. Yeah, we're good. Now we'll get into the ALS decomposition. Yeah, good. Thank you, Vlad. I think that is correct. So now we're going to use the implementation of ALS. So that is, in a way, an advantage of using these frameworks that, I mean, if you were to implement ALS by yourself, that would take you some time. But the fact that there is an implementation and presumably is already efficient, you don't have to spend a lot of time doing that, but instead thinking about how can you get your data in the right format, and how do you interpret the results, which I find is where I spend most of my time actually, trying to understand the results and whether they make sense or not, and then from that sort of repeat the process over and over. So if you don't have to think about this particular implementation, then you can spend more time understanding the results. Of course, there are times where it's important to do your own implementation, or you might find that, for instance, this implementation is not correct or is not appropriate for the sort of data that you have. So then you have to do your own. But initially, um, for sort of having a baseline, it's good to have some benchmark that you can run simple algorithms off the shelf and don't have to worry about then later implement the full algorithm, and maybe find that you have bugs in your implementations and sort of waste time there. But I strongly believe that it's important that you know what the algorithm is doing, and at least once in your lifetime implement some of them. So certainly the syntax is maybe we can get into that. Okay, so the syntax for the ALS is very simple. As always, I like to make sure that I open the API and make sure they understand all the parameters. So there are two different libraries. There is ML, which is the one that is going to take over. MLlib, MLlib's still there. So MLlib ALS. And for this particular, we're using this one, MLlib ALS. And right, so this is what we would expect. We expect the inputs are to have a ratings, which is an RDD, and it's in the format that we have been working: user ID, product ID, and rating. The number of iterations. So this is how many times you try to minimize the matrices. Lambda is the penalty coefficient, and I think that is exactly what we have here. So we have the training RDD, ranks. So the ranks is the dimension of the matrix. So remember that we have we're decomposing the matrix into we're decomposing this user by movies matrix into a users by rank times rank by movies length. So then at the end, if we do some, what the rank is the dimension of this matrix here and the dimension of the matrix, the movies matrix in this direction. So then, of course, we could in principle vary that result. And so in this particular, we chose 4, 8, and 12. It might be that you do a different scan. So maybe you don't do 4, but you do 10, or whatever might be your case. So I guess that is part of the hyperparameters that you would be tuning. And then you start training your model. So then once you enter all the parameters of the model, you would train, and then you would predict. And notice that we're predicting not in the testing, not in the training, but in the validation data sets, which is the second partition that we did. And then we calculate the error in that particular validation RDD. And why that is the case is because we are trying to find which one of these parameters, which one of the ranks is the best parameter. So this is our hyperparameter space. So in this case, we chose only to look at this one parameter, the rank, but we can certainly could have chosen to do many other parameter, whole hyperparameters, as we will see in other algorithms. So then in that case, instead of doing a linear search, what you would do is a grid search. And what that would look, so let's look, right? Search. So what you would do effectively is say if you have a parameter space that is only composed of 2 parameters, you would put points on each one of those grids, and then you would scan the full grid, trying to find within that grid what is the set of parameters that would minimize your function, that would minimize your function. So in this case, we only do it in 1 dimension because we only have 1 hyperparameter, which is ranks. But when you have multiple dimensions, then what you do is a grid search, and as well. And I think we will get into that with some of the other algorithms. But in a way, here we are building our infrastructure to iterate over each one of the hyperparameters. It could be the case that gets very complex. So for that there is a built grid search that we will get into it, and then from this particular minimization we see that the rank for which the error is the smallest is then rank 4, right? If we compare, yes, if we compare them with all the other ones. So in this case, all the rank 4 was able to do the same or have similar smaller error than a higher rank. So I think this result might be counterintuitive, because you would expect if you have a higher rank, you will have a smaller error. So sometimes just looking at the data or performing this sort of experiments in the data is sometimes goes against your intuition, and I think that's awesome that we can just evaluate things with data, not by just gut feeling. So then at the end that we have chosen that particular hyperparameter for, we can then train the model again with training data, and then we will evaluate this particular model with the testing data, and that's what we're doing here. We convert the testing RDD into the format that is expected, and then we predict all the values. So if we go back to the here. Oops. Predict all accepts an RDD in the format user ID, movie ID. And that's why we have to do this transformation first. So we're here now. We're in the testing side. All right. So any questions up to this point? I think we're close to wrapping up for the session. But the next one is comparing your model, and what it does is you become one of the users. So what you do is you enter ratings, and then you add those ratings to the training matrix, and then you see what recommendations would be to a user that is new to the training. So of course you would have to train the algorithm again. So that's what we do in this part, where we train the exact same with the exact, or I guess with the ratings appended, with the new ratings appended to everything else, and then we find the value that minimizes the error. So almost the exact same stuff as before. And then from that, the beauty is that we can find what would be the rating for movies that we have not seen. So using the predict all on movies that are not in that list of rated movies, then we can find what is the prediction. Then in principle, we could sort all those unrated movies um, by the rating, and then serve those as recommendations for each one of the users that don't have rating. So in a way, this was a fun part of the exercise to make it a little personal. Um, any questions up to this point? All right, I think we had some questions for you. All right. So there are different ways of doing recommendations. So I'm gonna post um, a question, and hopefully you guys would be able to answer it. So the question is, can you mention some difference between item to item and content-based filtering? So this is, I guess, for the people that already have done recommender systems, and which is a topic that is useful sometimes. So if you have some idea of what this means, please try to answer, so we all get some value from there. Oh, yeah, okay. Google would always give us the answer, right? Stack Overflow. Yeah, thanks. Can you try to put it in a few words from what you understood from there, Vlad? All right. So when it comes to item, what you're finding is a way to describe each item, and then doing things like cosine similarity that we saw last time, and you try to find items that are close within that vector space. In the case of collaborative filtering, which is the one we talked about today, what we're trying to find is those relationships that occur when the user interact with the item, which is that is the main difference. That in a way, when we're using the uh, the content base, we're adding that interaction of the user with the items. All right. Any more questions up to this point? Otherwise, we can leave it like this and go on for the next session. Also, if you have any suggestions, please let us know at this point. And also, please remember to do the videos. We have already received several of them, really good videos. So we're looking forward to your contributions, and this, in a way, would help us understand and showcase some of your questions and some of understanding where you're coming from and what you've been getting from the experience so far. Correct. Yeah, Augustine brought a very good point. Sometimes, if you don't have ratings, what do you recommend? So yes, that's when you might go and use things like item to item recommendation, content based recommendations. Yeah. All right, as I see, there's no more questions. So thank you everyone for participating, and we'll be sending instructions for the next round of analysis or the next lab and exercise in the next few days. Please make sure to keep asking questions here in the Slack channel. Remember to do your videos, and I'll see you next week.